Okay, this is the fifth mini lecture in stellar structure and evolution. We talked about how we think very low mass stars will eventually end their main sequence lives. The thing about this is it's all theory. The universe has not lasted long enough for stars of this mass to have ended their lives. They are the misers of the universe. They pretty much go on burning virtually forever. But they will eventually run out of hydrogen fuel, and when they do, we think that they will merely shrink up because they're totally convective and well mixed. They will not go through a giant stage, and they will become white dwarfs. Now, the white dwarfs we see in our galaxy today did not come from these very low mass stars. They came from medium mass stars. We'll get to that later. Let's just talk briefly a little bit, though, about white dwarfs and their properties. So a white dwarf is the end state of both a very low mass and a medium mass star. As I said, none of the white dwarfs that exist today came from stars less than probably about 0.6 solar masses. Maybe even more than that, maybe 0.8 solar masses. But stars up to an initial mass of 8 solar masses, we think will eventually end up as a white dwarf. They have the mass of a typical medium mass star. However, they only have the size of the Earth. So if you take that kind of mass, say 6/10 of the mass of the Sun, and you divide it by the volume of a sphere the size of the Earth, you are going to get a ridiculously high density. About 3 times 10 to the 6th grams per cubic centimeter. A typical rock has a density of 3 grams per cubic centimeter. So we're talking about a density 1,000,000 times more dense than rock. To put it another way, if you had a teaspoonful of material, which is approximately equivalent to, say, a sugar cube of material of white dwarf star, it would weigh 15 tons. White dwarfs are not really technically stars. They are things that used to be stars. There's no nuclear energy produced. They basically just shine by the stored up heat from the former starhood and from the gravitational collapse that turned them into white dwarfs in the first place. One analogy I heard that I kind of like is that you can think of white dwarfs as sort of retired stars. They've saved up their entire life of heat, a little bit of heat, so now they are spending that extra excess heat that they saved up. Okay. Another thing that's interesting about white dwarfs is as a star or a white dwarf shrinks and gets smaller and smaller, the gravity gets stronger and stronger. Okay, if you remember, the law of gravity was proportional to mass, but also inversely proportional to the radius of the object. So if you were standing on a shrinking star and you weighed 10,000 newtons, if it shrank to half that size, you would weigh 4 times as much, or 40,000 newtons. It turns out that the white dwarf is 100th the radius of a normal star, so that means that its surface gravity would be tens of thousands times greater than that of a regular star. We're going to see that a white dwarf is not by any means the most exotic or severe outcome of the end of a star's life. White dwarfs, however, were discovered long before they were understood. This is a picture of the star Sirius, the brightest star, the star with the greatest apparent brightness in our sky. The star Sirius, the dog star, is out generally during the winter, and you can see right here a little companion. This companion is the first white dwarf that was ever discovered back in the late 1800s. It has a very high surface temperature, but a very low luminosity. If you remember the HR diagram, if you have a high surface temperature, meaning it's on the left-hand side of the diagram, and a low luminosity, which means it's on the bottom of the diagram, that conspires to make it very, very small. Okay? So astronomers in the 1800s understood that this star, or what seemed to be a star, was actually only about the size of the Earth. Because when you figure out its temperature and its luminosity, that has to be the answer. So it is the mass of the sun, and therefore a very high density, as we saw in the previous slide. Again, this was known long before we understood anything about electrons and degenerate electron pressure, the pressure of those overcrowded electrons that hold up the white dwarf star. Okay, now let's talk a little bit about how medium mass stars eventually turn into white dwarf stars. They go through many, many different phases before they do. Since there's no convection in the core, the helium buildup occurs and the star turns into a giant. So basically the giant phase that we described to you in the previous mini lecture happens. But now you have a giant star that is burning helium in the core with a shell of hydrogen fusion around it. The helium is burning into carbon, and the hydrogen is burning into helium in the surrounding shell. And you're going to get a buildup of carbon in the core. Okay. So the core then is contaminated with carbon. The core contracts. It heats up a surrounding shell of fresh helium. Around that, you have a shell of fresh hydrogen from the envelope of the star. And so you end up with this sort of onion skin layer thing of fusion happening. Okay, well, the carbon-oxygen core in the center, the carbon core in the center, generally may or may not get hot enough. We don't think it, in the medium mass stars up to about 8 solar masses, we don't think that the carbon core will ever reach 600 million degrees that is needed for carbon fusion. So you end up with a carbon core, which will be inert, a helium-fusing shell, and a dormant hydrogen-fusing shell around it. The size of the star, the star will bloat out to about the size of the Earth's orbit around the sun, or slightly less. And then you end up with a red giant star. Now, this red giant star will slowly lose its outer envelopes. It will be blowing these envelopes away by the intense radiation pressure of these helium and hydrogen burning shells around the core in a massive stellar wind. So as the outbound envelope eventually moves into space, eventually the core will get exposed. The envelope thins out, exposing the hot carbon core. The surrounding gas stays ionized and continues to be ionized by the radiation of the central core that is exposed. And what you end up with this is with this sort of ring effect. Okay, a glowing ring of gas. And this is called a planetary nebula. The term planetary nebula is somewhat misleading because it has absolutely nothing to do with planets. The reason it's called a planetary nebula is historical. When they were first discovered, the great astronomer William Herschel thought that they looked like the disk of distant planets through his telescope. And so he just used it as a descriptive term. That, oh, these nebula, well, I know that they're nebulas, but they are sort of round, so they look like planets, so I'll call them planetary nebula. Unfortunately, when you tell people about planetary nebula, they often think it has something to do with the formation of planets. It does not. Okay. Now, the real excitement happens in high-mass stars, stars greater than about 8 times the mass of the Sun. They go through all the same giant phases that we talked about up to now, but once they get to a carbon core, okay, like we talked about in the previous medium mass stars, it doesn't just shrink to a white dwarf. It does get hot enough for carbon fusion. And then, depending on the mass of the star, it may go through other types of fusion. You'll have a carbon fusion core surrounded by a shell of helium and hydrogen fusion. And later on, if it's high mass enough, it will fuse even heavier elements in the core. Okay. But this desperation move by the star to continue to build up by burning heavier and heavier elements eventually runs out of luck. fusion becomes less and less efficient the heavier the element you have. Helium fusion is less efficient than hydrogen fusion. Carbon fusion gives you less energy than helium fusion. Neon fusion gives you less energy than carbon. Oxygen less than neon, etc. Once you get to iron, you are at the breaking point, because iron doesn't give you any energy at all if you try fusing it. Okay, by this time, our massive star has bloated out to the size almost of Jupiter's orbit. So we're talking about a massive supergiant star here. Iron has the most tightly bound nucleus, and so when you try to fuse iron, okay, the star doesn't know this. The star doesn't have a knowledge of nuclear physics, so it tries to fuse iron anyway. That's basically what has happened. Every time the core runs out, the core is contaminated with waste, it collapses, it gets hot enough to try to burn that waste. It has succeeded all the way up to iron, and when it tries to fuse iron, instead of giving off energy to stop the collapse or stall the collapse, it actually absorbs energy, which speeds up the collapse. So the collapsing iron core then tries to fuse iron. The iron fusion sucks up the energy and speeds up the collapse. You have a catastrophic runaway collapse. Basically, you're in for a gigantic train wreck. The rebound of material in this natural collapse of the core, this train wreck, which happens in a fraction of a second, blows up the entire envelope of the star, and you end up with a supernova. This is actually called a Type II supernova. A Type II supernova is the explosion of a massive stellar core at the very end of its life when iron is contaminating the core. Here is a picture of the first naked eye supernova that had been seen in about 400 years in the Tarantula Nebula in the southern skies. This was in 1987. There hasn't been another naked eye supernova since. We are actually overdue for one. This was the progenitor star of the supernova. It was actually a blue supergiant. Supernovas are so bright that they can be seen in distant galaxies, and in fact, we now use other types of supernova explosions, which are called Type 1a supernovas, to judge the distances to galaxies. Type 1a supernovas are basically white dwarf stars that accrete material from a companion star, and once they get to a critical mass, they end up blowing up. And those types of supernovas are actually more uniform, and so we can use them to judge distances to galaxies, but we'll get into that in the next unit. Okay. In fact, these Type 1a supernovas, here we go, are basically happening in a different way. You can often have a binary star system that is so close together that you can have material from a giant star actually being sort of sucked up by this white dwarf. And when it gets sucked up by the white dwarf, the mass builds and builds and builds until eventually you can get a detonation. Okay. So these are Type 1a supernovas. They're actually brighter than the Type 2 supernovas that we talked about. When I think of supernova, I almost always think of the Type 2, the end of a really massive star's life. Now, a supernova can briefly outshine an entire galaxy of stars. Here you see a supernova right next to a very, very bright galaxy. It's probably in the outer reaches of this galaxy. The incredible thing about supernovas is they are basically responsible for all the elements in the universe heavier than iron. And they are also responsible for all the elements heavier than helium that are ejected into the galaxy to get recycled into new stars. And this is a very, very stunning thing to understand. So actually, I think I will save that for part 6.